Okay, I wrote on the board that we're going to be having a quiz on Tuesday on this chapter. After this chapter, we'll go into curve sketching, and then you guys will write your next exam. So a lot of the stuff that we're talking about in this chapter, we'll be using to help us sketch curves, sketch the graphs of different functions. Okay, so we've learned about finding intervals of increase, decrease. We've learned about finding where our local max or mins are, and in some cases those are absolute max and mins. So obviously those can be applied to graphing functions. So that's what we're working towards. So this lesson talks about the mean value theorem. If f is continuous on the closed interval from a to b and differentiable on the open interval from a to b, then there is a number c in that interval from a to b such that f prime c, which is the derivative, will equal f at b minus f at a all over b minus a. So that formula on the right, that's our slope formula. So there's a place where the derivative will equal the slope. So c is a point such that the slope of the tangent line through c is parallel to the chord AB. So you're going to have 2 points here, 2 points on a curve, and if you connect them, you get what's known as a chord. So there is a place somewhere on the curve where the tangent line is parallel to that chord, and that's what we're going to be finding. For each of the following functions, determine if the mean value theorem applies on the given interval, and if so, find all possible values of c. If not, state the reason why. So in most cases, a reason that it might not be is because it's outside the domain that we're given. Okay? So that's one possible reason why the mean value theorem may not apply in that situation. But we'll see that as we go through. So once again, there is a place somewhere where the derivative, which remember gives you the slope of the tangent, so where the tangent line is parallel to the chord going through the point -2, x equals -2, and y equals +2. So we might start by first finding the slope of that chord by applying the slope formula. So the slope of the chord is what we're going to start finding. Now to do that, we're going to have to know what f at -2 and f at +2 is. Because the slope formula says y2 minus y1 over x2 minus x1. We have our x2 and our x1. We need to know what y2 and y1 are. Right? So we need to find out what the value of the function is at each of these endpoints, each point on the chord. So f at 2 would be 2 cubed plus 2 times 2 squared minus 3 times 2 plus 1. So that'll be 8 plus another 8 minus 6 plus 1. So 8 and 8 is 16. Take away 6 is 10. Plus 1 is 11. Then we need to find f at -2. So it'll be -2 all cubed plus -2 all squared minus 3 times -2 plus 1, which will be -8 plus 4 plus 6 plus 1. So that'll be 3. No, sorry. Oh, I forgot the 2 in front of that. So that should be 8. So that gives us a value of 7. So again, this theorem says that, the mean value theorem says that there is a place somewhere on the curve where the tangent line, which is defined by the derivative is 3x squared plus 4x minus 3, where the derivative equals the slope of the chord, meaning that the tangent line, which the derivative tells us the slope of, is parallel to that chord. So now we need to find the slope of that chord. Again, we're going to use our point -2, 7, and the other point is 2, 11, and apply the slope formula to those 2 points. y2 minus y1 over x2 minus x1. So 3x squared plus 4x minus 3 will equal 11 minus 7 is 4 over 2 plus 2, which is also 4. So that's the slope of the tangent. So we need to know where the derivative equals that, which again will tell us what point on the curve, what value of x exists such that the tangent line will also have a slope of 1. So if you subtract the 1 from both sides, because we're going to solve the quadratic, and we need to make it equal to 0 before we can do that. And we solve this by factoring. And I think -2 plus 2 will work. The outer product is 6x, the inner minus 2x, that gives you the 4x in the middle. The front terms multiply to get 3x squared, the last terms multiply to get -4. So our solutions will occur where each factor equals 0. And there's our 2 places on the curve where the tangent line is parallel to the chord that goes through x equals -2 to x equals +2. Now, if we look up above, once again, it says that f is continuous on the closed interval from a to b. So that just means that there's no non-permissive values. If it's continuous, there's no breaks in the graph, which it is because it is a polynomial function. But also has to be differentiable on the open interval from a to b. So the value of a here is -2, the value of b here is +2, right? This is the value of a, and this is the value of b. And if we look at this, it's the open interval from a to b. So that means if one of your answers is either a or b, according to this theorem, we can't use it, which is the case here, because we got -2 as one of our answers, but that also corresponds to the first x value on the curve. So because that is outside the open interval, that point does not work. So this point is not in the open interval. So you would not consider that point as being one of our solutions. Okay? Now, a and b can be any 2 numbers you want, right? The theorem just says that if one of your answers is not within the open interval from a to b, then you cannot consider it as being part of the solution, because there has to be some restriction on what part of the graph you're looking at. Okay? So it just so happens in this case that that value of -2 is not within that open interval. So the second one then, again, this is a polynomial function, so there's no restrictions on x, so you don't have to worry about the function being differentiable throughout this domain. But we want to find where on this graph does the tangent line, is it parallel to the chord going through x equals -1 to x equals 3? So like we did before, we need to find out what the y values are at -1 and 3. Yep. So from x equals -1 to x equals 3, you're going to put those 2 points on the graph and you're going to draw a line through them. That's a chord. And so your tangent line is going to be parallel to that chord, have the same slope. That's what we're finding out. And that's why we take the derivative, because the derivative gives you the slope of the tangent. So negative 1 all cubed is negative 1 times negative 2, plus negative 1 all squared is 1, plus 4 plus 2. So 2 plus 1 is 3, plus 4 is 7, plus 2 is 9. And then we want to find out what f at 3 is. So 3 cubed is 27 times negative 2 is negative 54. 3 squared is 9, minus 12 plus 2. So when you combine all those, you're going to get a value of negative 55. Negative 54 plus 9 is negative 45. Take away 12 is negative 57 plus 2, negative 55. So again, the derivative, which is negative 6x squared plus 2x minus 4, that would give you the slope of the tangent. It's got to be parallel to the chord going through x equals negative 1, or the point negative 1 comma 9, and the point 3 comma negative 55. So our tangent line will be parallel to the chord going through those 2 points, which means it has to have the same slope. So we'll find the slope by going y2 minus y1 over x2 minus x1. So negative 55 take away 9 is negative 64 over 4, which is negative 16. Right, that's the slope of the tangent, which is also the slope of the chord. So if you add the 16 to both sides, and then we need to solve this quadratic. Now there is a common factor we could take out of negative 2. But that quadratic that we're left with is not factorable. It doesn't mean there's no answers, it just means that they are not integral. So we will go to the quadratic formula. Remember, that can always be used to solve a quadratic. Negative b plus and minus the root of plus and minus the root of b squared minus 4ac all over 2a. So we are finding the solutions to that quadratic. 3x squared, take away x, take away 6. The value of b there is negative 1, so negative 1 becomes positive 1. Plus and minus, again, the b, which is negative 1, is all squared, minus 4 times a times c all over 2a, which will be 6. So if we work out the value of the discriminant, remember, is what's under the radical. So negative 1 all squared minus 4 times 3 times negative 6 is 73. So we're going to have 1 plus and minus the root of 73 all over 6, which, if we find out what those are as a decimal, approximate values, 1 plus the root of 73, close the bracket for the numerator, divided by 6, That's approximately 1.59. And then the second one will be when it's 1 takeaway, root 73, all over 6. So negative 1.26 approximately. But we also have to look back at what our interval is. Our interval goes from negative 1 to 3. And that negative 1.26 is outside that domain. So we have to disregard it. This is outside the domain. So it's not one of our answers. There's only one spot where that works, and that's at 1 plus root 73 all over 6, or approximately 1.59. Now for number 3, it's a rational function. That rational function, though, has a non-permissive value of positive 3. There would be a vertical asymptote there, and positive 3 is in the domain that we're given here. So this graph would not be differentiable at 3. It's not continuous at 3. So therefore, it does not apply. Remember at the top we said that f must be continuous on the closed interval from a to b. And in this case, it's not continuous at positive 3, which is in this interval. So we would say in this case, the theorem does not apply because f is discontinuous at 3. But for number 4, it's the same function. What's changed, though, is the domain. This domain goes from negative 2 to 2, so the function is continuous in that domain because, again, our non-permissive value is at 3. So in this case here, it will work. So we need to find out what f at negative 2 and positive 2 is. And for negative 2, it doesn't really matter what the denominator is because the top is 0. So that will be 0. The point negative 2 comma 0 is our first point. F at positive 2 is 4 over negative 1, which is negative 4. So that's the point 2 comma negative 4. So now we have to take the derivative, which we need to use the quotient rule for. Derivative of the top times the bottom, minus the derivative of the bottom times the top. All over the bottom squared. And that has to equal the slope of the chord. So y2 minus y1 will be 0 minus negative 4 over x2 minus x1. So simplifying the derivative, it's going to be x minus 3 minus x minus 2 all over x minus 3 all squared. And that will equal 4 over negative 4. So we can say then that when we simplify the derivative, the x's cancel. We're going to get negative 5 over x minus 3 all squared. Has to equal negative 1 or negative 1 over 1. And I write it like that because I am going to cross multiply to solve for x. So negative x minus 3 all squared will equal negative 5. You can divide both sides by negative 1. And then when we solve for x, we take the square root of both sides, which will give us plus and minus root 5 on the right, and then add 3. So again, this gives us two places on the curve where the tangent line is parallel to the chord. If we use our calculator to find out what the approximate values of these are to make sure that they fall within the domain, we have 3 plus the root of 5. So approximately 5.24. And 3 minus the root of 5. Approximately 0.76. And if we look at our domain is between negative 2 and positive 2. The 5.24 is outside that domain. So that one doesn't work.
You may think that the mean value theorem is just this arcane theorem that shows up in calculus classes, but what we will see in this video is that it has actually been used, at least implicitly used, to give people speeding tickets. So let's think of an example. So let's say that this is a toll booth right here. You're on the turnpike, and this is a toll booth at point A, and you reach it at exactly 1 p.m. and the highways, computers and stuff register that. Let's say you have some type of one of those devices so that when you pay the toll, it just knows who you are and it takes your money from an account someplace. So it sees that you got there at exactly 1 p.m. And then let's say you get off of the toll highway, the turnpike. Let's say you get off of it at point B and you get there at exactly 2 p.m. I'm making these numbers very easy to work with. And let's say that they are 80 miles apart. So this distance right over here is 80 miles. 80 miles. And let's say that the speed limit on this stretch of highway is 55 miles per hour. Speed limit is 55 miles per hour. So the question is can the authorities prove that you went over the speed limit? Well, let's just graph this. I think you know where this is going. So let's graph it. So let's say this right over here is our position. So I'll call that the S-axis, S for position, and that's going to be in miles. And S is obviously S doesn't really stand for position, but P, it kind of looks like rho for density, and D we use for differentials for distance or displacement. So S is what gets used for position very often. So let's say S is our position, and let's see, this is T for time. T for time, and let's say this is in hours. And let's see, we care about the interval from time going from time 1 to time 2. I'm not really drawing the axes completely at scale. Actually, let me just assume that there's a gap here, just because I don't want to don't make you think that I'm drawing it completely at scale, because I really want to focus on this part of the interval. So this is time equals 2 hours. And so at time equal 1, you're right over here. Let's say this position is, we'll just call that S of 1. And at time 2, you're at this position right over here. You're right over there. And so though your position is S of 2, you're at that coordinate right over there. And that's all we know. That's all we know. Well, we know a few other things. We know what our change in time is. It's 2 minus 1. And we know what our change in position is. We know that our change in position, which is equal to S of 2 minus S of 1, minus S of 1 is equal to 80 miles. The change in position is 80 miles. So let me write that. And we'll just, for simplicity, assume it's a straight highway. So our change in distance is the same as our change in position, same as change in displacement. So this is 80 miles. 80 miles. And then what is our change in time? Over our change in time, well, that's going to be 2 minus 1. 2 minus 1, which is just going to be 1 hour over 1 hour. Or we could say that the slope of the line that connects these 2 points, let me do that in another color, the slope of, that's the same color, the slope of this line right over here, is 80 miles per hour. Slope is equal to 80 miles per hour. Or you could say that your average velocity over that hour was 80 miles per hour. And so what the authorities could do in a court of law, and I've never heard a mathematical theorem cited like this, but they could, and I remember reading about this about 10 years ago, and it was very controversial. The authorities literally said, look, over this interval, your average velocity was clearly 80 miles per hour. So at some point in that hour, and they could have said by the mean value theorem, at some point in that hour, you must have been going at exactly 80 miles, at least, frankly, 80 miles per hour. And it would have been very hard to disprove because your position as a function of time is definitely continuous and differentiable over that interval. It's continuous. You're not just getting teleported from one place to another. That'd be a pretty amazing car. And it is also differentiable. You always have a well-defined velocity. And so I challenge anyone, try to connect these 2 points with a continuous and differentiable curve where at some point the instantaneous velocity, the slope of the tangent line, is not the same thing as the slope of this line. It's impossible. That's the mean value theorem tells us it's impossible. So let me just draw. So we can imagine, let's say, I had to stop to pay to get to kind of register where I am on the highway. Then I start to accelerate a little bit. So right now my instantaneous velocity is less than my average velocity. I'm accelerating the slope of the tangent line. But if I want to get there at that time, and especially because I have to slow down as I approach it, as I approach the toll booth, the only way I could connect these 2 things, well, let's see, I'm going to have to, at some point, I'm actually going faster than the 80 miles per hour. And the mean value theorem just tells us that, look, if this function is continuous and differentiable over this interval, continuous over the closed interval, differentiable over the open interval, that there's at least one point in the open interval, which it calls C. So there's at least one point where your instantaneous rate of change, where the slope of the tangent line is the same as the slope of the secant line. So that point right over there, that point looks like that right over there. And so if this is time C, that looks like it's like at around 115. The mean value theorem says that at some point there exists some time where S prime of C is equal to this average velocity, is equal to 80 miles per hour. It doesn't look like that's the only one. It looks like this one over here. This could also be a candidate for C.
So the moral of the story is don't speed.
Let's go test this, Brian. Let's go 50 over in a school zone.
Okay, so there is a worksheet there that you can work on. The answers for the odd questions are given, so you can check. I will post the solutions to Google Classroom, so you can also check them there. So remember, on Tuesday, We will have a quiz on this chapter, and we'll also start the next chapter on curve sketching. Okay?